We got about another minute to go until we officially start.
Okay.
Awesome.
great.
And Vivian, how does the weather for you today?
Gorgeous. Really lovely.
Nice.
All right, it's 6 o'clock. And so hello, everyone, and welcome to the July NASA Night Sky Network member webinar. We're hosting tonight's webinar from various domiciles for the Astronomical Society of the Pacific in San Francisco, California, and other various places. Dave is way up there, closer to Canada than to anything else in New York. We're very excited to present this webinar this evening with our guest speaker, Dr. Teresa Nieves from NASA's Goddard Space Flight Center. Also, welcome to everyone who's joining us on the live stream. We're very happy to have you with us. These webinars are monthly events for members of the Night Sky Network, though we look forward to continuing to live stream these into the future. For more information about the NASA Night Sky Network and the Astronomical Society of the Pacific, either Vivian or Dave will put some links into the chat. Before we get to Teresa, here is Dave Prosper with just a couple of announcements.
Okay. Hi, everyone. So I just have one brief thing, and some of you may know this already. We have some new resources to help with your virtual events. We've added the event type virtual event to the main calendar, which is really handy for folks that are looking for online astronomy events that are kind of location independent, that they can join via computer, as you're doing right now. We've actually heard of some folks joining from all over the world. So if you've posted events to your Night Sky Network calendar and you want to make them available to the virtual event listings as well, you can just go back to that event and edit it. And instead of an observing event or club event or community event, check the new virtual event, save it. It'll pop onto that virtual event calendar. And the virtual events also show up in the main Night Sky Network calendar as well. And if you don't want the event seen by everyone around the world, then you can set the privacy for these virtual events to members only as well. The trick with these is the virtual events do not use a location. So if you try to create a virtual event, it will complain if you try to set a physical location. So, more options for everyone, always fun. And speaking of them, we also have new resources to help with them. In particular, a page full of best practices and recommendations for holding your online virtual style events. And if you're actually now holding in-person events, we've also created a little flyer to help with some best practices, mostly, sanitation, distancing, that kind of thing. And I'll post links to all of these resources in the chat in 1 second as I scroll down to get them all.
I was just posting them all.
Oh, cool. Thank you. Thank you, Vivian. And with that, we're done. And Brian, back to you.
All right, thanks, Dave. So for those of you who are on Zoom, you can find the chat window and the Q&A window at the bottom edge of your Zoom window on your desktop. Please feel free to greet each other in the chat window or let us know if you're having any technical difficulties. You can also send us an email at nightskyinfo@astrosociety.org. If you have a question you would like our guest speaker to answer, please type it into the Q&A window. If it goes in the chat, there's a pretty good chance it's going to get lost, and there will be a much better chance that we'll be able to get to it if it's in the Q&A window. Also, for those of you that are chatting, make sure that you go down there to the little blue button and select all panelists and attendees so that everyone can see your greeting. So let me hit this recording button. All right, so welcome again to the July webinar for the NASA Night Sky Network. This month, we welcome Dr. Teresa Nieves to our webinar. Dr. Nieves is a research astrophysicist in the Heliospheric Physics Laboratory in the Heliophysics Science Division for NASA. In 2018, she started to work as the NASA project scientist for the Solar Orbiter Collaboration. And starting this year, she is serving as the NASA Deputy Project Scientist. Her research efforts at Goddard are motivated to understand the nature of coronal mass ejections and their interactions with the solar wind, planets, and the Earth. Her main contributions to the field has been providing a new perspective to the theoretical analytical flux rope model for magnetic structures embedded in the interplanetary CMEs. So, you know, that's pretty great stuff. She was a high school teacher for 7 years. I have a fondness for teachers, having been one myself. In Spain, before her journey to the United States with a commitment with a new generation of scientists. She's currently raising a young family of 2 girls, and in their spare time, she enjoys reading, walking, watching shows, and traveling. Maybe not so much traveling these days. Please welcome Dr. Teresa Nieves.
Thank you very much, Brian, and thank you all for having me tonight. It's a huge pleasure to share with you all the adventures that we are having with Solar Orbiter. Let me share my screen, right? Okay. Let me see. Okay. Can you see my screen now?
It looks great.
Thank you very much. So, right, so I'm Teresa Nieves-Chinchilla. I'm the NASA Deputy Project Scientist for the Solar Orbiter collaboration. And I'm here tonight, here in DC, to talk about Solar Orbiter, which is the latest mission, solar heliospheric mission for these 2 agencies, for ESA, a European Space Agency, and NASA. And it's a collaborative mission, which has the goal to investigate the heliosphere. So tonight I'm gonna divide my presentation, let's say, in 3 blocks. And the first one, I'm gonna talk about the science, which is actually which motivate in these missions, and Solar Orbiter, obviously. And then I'm gonna talk later about the mission itself, the spacecraft, and the journey that we have been going through to get this mission moving. And then I'm gonna share with you the latest images and observations. The first flight that we released a few days ago to the public. And it's so exciting to share also tonight with you. So you are astronomers, all of you. And then I know you are very aware that we actually live in the atmosphere of one star, the sun. And this atmosphere is actually a bubble of magnetized plasma that envelops the solar system and define the boundaries with the interstellar medium. This bubble, the heliosphere, is created by the solar wind. The solar wind flows out in radial direction all the way from the sun and sometimes reach the Earth. We know all that the sun is our main source of energy, but in a way we are also electromagnetically connected with our star, and we'll see how now. So again, you're astronomers, you know even more than me probably about these facts. We know that, so I'm gonna go very quickly. Our sun is a young star. It's not so old, it's not so young, it's just in the mid-age. 44.6 million years ago, it was created, and it's gonna be probably around for another 5 billion years. It's located in the Milky Way, sharing the space with 250 billion of similar stars. And the orbit, the periodicity of this orbit is, you know, this big number. So we are just aware of this tiny portion of the orbit of our star around the core of the galaxy. The rotation around its axis is 27 days, and it's an average number, and it's not so precise, so I will be back to this number later. but we know that it is 109 times larger in size than our Earth. In terms of the mass, you can put a 2 and 30 zeros right after the 2, and these are kilograms that are mainly concentrated in the core of the star. And we know for sure that it counts for 99% of the solar system mass. According with the observations, we estimate that the core of the sun fuses 620 billion hydrogen tons into 606 million helium tons per second. The remaining mass is converted into an energy based on this formula, very well known. The energy released in the core takes around 200,000 years to reach the surface, but the light from the surface get the Earth in just 8 minutes. The sun global magnetic field, which is dominate the heliosphere, and this is for sure, we know that, is generated by something similar to the magnetic dynamo. And I say something similar because the magnetic dynamo is a very good model, but there are pieces in the understanding of this dynamo that are lacking in our, and we need to find exactly where it's lacking. So for instance, when I was talking about my screen is in this side, sorry, the big screen, so I'm looking at the camera all the time. I have to apologize. But so in the, when I talk about the periodicity of the rotation around the axis, the periodicity is not the same at the equator, but in the poles of the sun. It's actually is lower in the poles than in the equator. This difference in the speed of the plasma generate some kind of currents, and the currents and the gradient in the speed and the currents accumulate the energy, the magnetic energy, in what we call sunspots. Sunspots are highly magnetized plasma that accumulate a lot of energy, and they are dark because the temperature is colder than the surrounding plasma. We have been counting sunspots for years, centuries. We know, all astronomers have been counting, right? So, and we, at this point, we know that more or less the number of sunspots in the sun change with the time. And the periodicity on the numbers, these cycles, change every around 11 years. However, if you check here in the plot, in the graphic at the bottom right, you can see the last 4 solar cycles. And you can see that the width of the solar cycle changed with the time. Actually, we don't know why the last few solar cycles are wider than the previous one. And we don't know why the number of the sunspots decrease with the solar cycle. So in this understanding of the solar dynamo and the behavior, how generate the magnetic field, our sun, there are pieces that still we don't really understand. And talking about energy, so if you see the movie in your right, you can see the big explosion in the sun. This is a movie and a series of observations from SDO. SDO is the Solar Dynamic Observatory. It's an observatory, a satellite that is located with the Earth in front of the sun, observing the sun and walking with the Earth around the sun. And this energy that is accumulated in the solar cycle need to be released in a way. And that one way to release such energy is through these coronal mass ejections, big explosions. This is one of the big ones. The one that is reaching the Earth could damage a lot of technology in the space. As you see, there is a plasma that is emerging from the sun. This is a prominence, and it can stay there for days, even weeks sometimes, and eventually, and we don't really know why, just emerge just evacuate the sun and initiate the propagation and the journey throughout the heliosphere. So these big explosions can be very damaging to the technology and in the space, even in the ground level in our Earth. Here we have another example. This is a movie this is very popular coronal mass ejections observed in 2000 by SOHO. SOHO is another satellite that is located with the Earth at the front of the sun, monitoring the sun. And this instrument is a coronagraph. And we are going to see more coronagraphs in this presentation. And coronagraph is just an artificial eclipse. With a disk, we cover the sun surface, the sun disk, to avoid the light from the disk blocks the light in the corona, and allow us, by blocking the sun surface, allow us to see the corona, to observe the faint corona around. And then if you have seen, you observe like two branches of increasing in the brightness, and eventually a big bubble coming to us, coming to the spacecraft. These white dots in the camera are energetic particles. These energetic particles saturate the camera and eventually can damage permanently, in cases, the camera. So these are very dangerous. And as you see from the beginning, they can just be at the spacecraft in less than 2 minutes. Here we have another example of a coronal mass ejections. This is actually several coronal mass ejections. And this movie is a composition of two spacecraft, two instruments, one from stereo. Stereo are two twins spacecraft moving away from the Earth around the sun at 1 astronomical unit, which is the distance between the sun and the Earth. And SDO is the previous, is located at the Earth and observing. So with the stereo, we have the coronagraph. So the disk, the black disk is the coronagraph. And we have located the image from SDO at the center, which is the sun. So we can track what is happening in the sun all the way in the corona. So as you see, these coronal mass ejections, we identify them by the increase in the intensity, in the brightness in the images, and also by this kind of bubble shape that are very particular and very interesting in our research, because they drag this magnetic field, special and helical magnetic field configuration. So which actually, like the coronal mass ejections, these coronal mass ejections evacuate from the sun and start a journey through the heliosphere. We think these are the big bubbles that are expanding. And these bubbles contain plasma and magnetic field, and sometimes even energetic particles and radiation. They move radially once they eject from the sun, they move radially from the sun, and they can go everywhere. Sometimes they reach the Earth, but because we have super shield, our super shield, the magnetosphere, protect us from this energy. And sometimes the coronal mass ejection just pass without, putting any energy in our system. But sometimes, and we know more or less why, but our shield, our magnetosphere, is broken and allow the entrance of these energetic particles and radiations. The good side of these events is we can see the aurora borealis or the northern lights. The bad side is, as our technology is more and more in the space, can be damaged by this energy. So our cell phones, our GPS may not work because of these events. So this is why, and more the society is being aware of the hazard from these events, how can we can be affected by this variability of the sun. And we have reports in the history. The first event, very well known, is the Carrington event. You probably have heard about that. And it was, Carrington was an astronomer, as you are all, and he was just counting sunspots and observing a group of sunspots. And he observed next to the sunspot an increase of the brightness. 2 days later, the aurora borealis increased. They observed a lot of aurora borealis, and also the telegraph system was affected by, some kind of currents that they don't know where they come from. So more recently, we have in 1921 a big, huge event that I will talk also later about a little bit more. It was 10 times larger than the event of 1989. However, because the technology, the society by that time was less advanced than in the 1989, the consequences in the societies were less, obviously. In the case of 1989, the city of Quebec was without power for more than 8 hours. So we have many events that we have been now, coming back and revisiting. And then we now can associate these kind of events with solar activity, with the variability in the solar system. So some cases are like these satellites. Some of them were lost forever just because of the solar activity. In the case of the space weather, when we talk about the space weather, we refer all the activity that goes from the sun in the solar system, in the solar wind, interplanetary medium, the magnetosphere, the ionosphere, the thermosphere, until to get the ground level. So we start to identify how, every, level or layer can be affected by the variability. We know that satellites can suffer drags, and we can have problem in radio communications, satellite communications, GPS transmission. We start to understand the consequences on the health in the astronauts, but also in the crew from the airlines. So we are starting to learn more about the consequences of the sun activity in our lives, in our regular lives. So for instance, in the report that I include here, they just estimate that in the case of having an extreme event similar to the one in 1921, 130 million of people can be affected without power. And the estimate and cost, it will be between $1 to $2 trillion trillion during the first year. This is an estimation, and we don't want to test, right? So we have eventually to be able to make predictions and to keep our technologies safe. Obviously, also is very important for something that is going to happen in the next few years. So with Artemis program in 2024, we are going to bring the first woman and the next man to the moon to develop the first colony of the humans in the space. And then we need to protect also our astronauts. So this is why it is important to understand our star, not just because we want to advance in the understanding, in the knowledge of our, the universe, our stars. It is also because we need to protect our technology, our societies. And so this is why we need to understand. We need to know how does the sun create and control the heliosphere. And this is a big question. So that's why Solar Orbiter is focused in these 4 questions. The first one is what is the origin of the magnetic field and what drives the solar wind? that create the heliosphere. We also want to know how does the solar dynamo work actually and drive connections between the sun and the heliosphere. We also want to understand how these huge coronal mass ejections drive the heliospheric variability and how the solar eruptions produce the radiation that fills the heliosphere. So these are the main questions that are, focused on Solar Orbiter and the teams and instruments. So, and here is Solar Orbiter. So Solar Orbiter will help to explore the sun and heliosphere connection. And the mission was launched in the past February 9 in 2020. This past February from Cape Canaveral. It was launched in a rocket Atlas 5 in the configuration 411. The phase of the mission, we have 3 phases, and I'll talk about that in the next slide, I think. So I'll talk about that in the next slide, but basically it's gonna be 10 years of mission. The cruise phase will be for 18 months. Then we have the nominal phase and the extended mission for 3 more years. In the orbit, we'll bring a solar orbiter to the closest distance of 0.28 astronomical units, being 1 the distance between the sun and the earth, 1 astronomical unit. And something very particular of this mission is that we are going to bring a solar orbiter out of the ecliptic plane. And I know you know what is the ecliptic plane. It's the plane that basically contains all the planets, more or less. So it requires a lot of energy to take the satellite out of the ecliptic plane. And this is going to be a big milestone for this mission. In the nominal mission, we'll get the 24 degrees of inclination in the orbit. And during the extended mission, we'll reach the 33 degrees. During all the mission, the in situ set of instruments, and in situ, I mean, when I say in situ, I mean instruments that are going to be taking measurements of the plasma, magnetic field, particles and waves around the spacecraft. And they are going to be working all the time, providing information and observation of what is happening around the spacecraft. And the remote sensing observations, and when I talk about remote sensing, I mean, and you astronomers know very well, are the instruments that provide observations from the light that they receive from the star. And these instrumentation are going to be on during the 3 dedicated windows that I'll talk in the next slide during the nominal mission. Something also very particular of this mission is the reduced relative rotation. It means that, if you think about SOHO, for instance, the satellite that it was monitoring the sun from the Earth, is more or less static with respect to the sun. So when we observe a structure, the structure is evolving at the same time the sun is rotating. So eventually it's going to be lost in the backside of the sun. And maybe if we stay there for 27 days, we can see later again back. But however, with Solar Orbiter, we are going to synchronize the satellite rotation, the orbit, with the rotation from the sun. So eventually we are going to be able to track structures over the time. So we are going to resolve temporal scales also. So and this is very critical for this mission. Mm-hmm. So here you see, when we launched Solar Orbiter, it was ballistically, literally, it was launched, and it was launched toward the Venus. So with the Venus, it's going to use the gravity assistance from Venus to alter the trajectory of the spacecraft and save a lot of energy, and then to get the orbit that is required in the mission. You know, with every gravitational assistance maneuver from Venus and Earth, we are gonna get the maximum approach to the sun and the inclination of the orbit, and then that is required for the mission. Here on your left, you can see the plots of the orbit, the change in the orbit with the time. At the top, you have the latitude. At the bottom, you have the distance. So we launch the distance to the sun. We launch at 1 astronomical unit, and we launched in February 2020, and we just passed the first perihelion now in June 15. So now we officially start the cruise phase, and we are gonna be during the cruise phase for 18 months and then we are heading right now to Venus to have the first, in December, the first gravity assistant maneuver. And then later next year, we are gonna have the second gravity assistant maneuver and start the nominal phase. Once we start the nominal phase, during each orbit, the spacecraft is gonna have 3 windows, as you see in the maximum and minimum latitude, and also in the maximum approach. In each window, all the remote sensing instruments are gonna be observing the sun. And later, once we pass the nominal, as you see in the latitude, in the inclination of the orbit is increasing over the time, and we are gonna get the 24 degrees by the end of the nominal phase. And starting with the extended mission, we are gonna get the maximum inclination of 33 degrees. In the nominal mission is when we are gonna get the maximum approach to the sun at 0.28 astronomical units. So again, this is a mission, it's a team effort between 2 agencies. Is for NASA, is a part of the Living with the Stars program. For ESA is the Cosmic Vision program. This is a mission led by ESA. ESA compromised to develop the satellite and the integration of the payload. 10 instruments, 9 of them were developed by the European states, and 1 of them was developed here in the US. And NASA provide the launch. And some of the sensors are in one of the payload instrument. So just mention here that the collaboration between these 2 agencies is a long-standing tradition of collaboration. We have 2 examples here. We have SOHO. SOHO was launched in 1995, and it was a mission for 2 years, and it's still alive. It's amazing, right? And then we had also Ulysses. Ulysses was a mission, a polar mission, as Solar Orbiter is, but it was just with in-situ instruments. So the difference is Solar Orbiter will provide by the first time images of the sun poles. And here is Solar Orbiter. So this is a 3-axis stabilized satellite. Is pointing toward the sun, and because we are gonna get this 0.28 astronomical unit of distance, we are gonna receive, the satellite is gonna receive 13 times the magnetic flux that any satellite or spacecraft receive at 1 AU. And this is why we need to protect the satellite and the payload, and we have this heat shield that is going to be pointing to the sun. So it is very interesting because this technology has been developed for this satellite. Is a carbon fiber composite with several layers of titanium, and is with a gap between layers that allow to dissolve the heat, and it's at the isolation, that some of the instruments require heaters to warm up the instruments and to, you know, get the nominal working level. Also, it's something very interesting in the satellite is in the heat shield, there are small windows through which each instrument can peek through and make the observations. Obviously, the instruments need to be also protected from the heat flux. Sorry. And also, it's very interesting because of the orbit is going to be changing in distance to the sun. We need to protect, for instance, the solar arrays. The solar arrays are articulate in a way that when we are very close to the sun, articulate to minimize the surface exposed to the sun. And as the spacecraft is going further from the sun, it's going to change to maximize the surface exposed and to get all the energy required for this system and subsystems in the satellite. Same with the high gain antenna, which is required to communicate with the ground segment here at Earth, and it can be articulated to protect when it's very close to the sun, or unfold when it's far from the sun and allow the communication with the spacecraft and Earth. Sorry. Let me begin. So here is the architecture of the spacecraft. So there are 10 instruments. And when we talk about collaboration, I put always here the flags because it's not about just 2 agencies. Are 10 instruments with leading each instrument by different countries, and even in each instrument there are, you know, consortiums of several countries. So this is a very, very strong international collaboration, and this is also, you know, challenging, but is being now here is, you know, something that we need to be proud of. So in the architecture of the spacecraft, you see that most of the instruments are behind the heat shield, but we have also some of them that are located in the boom, that they need to be isolated from the electromagnetic currents. I'm gonna go later through each of the instruments with the first light images. Let me move to the next one, which is the Periplus. Also, Solar Orbiter has been, you know, traveling. It was Airbus, which is the partner from ESA, was in charge of the spacecraft development and the integration of the payload, and it was carried out in the center that they have in UK. And here you can see one of the pictures from of the satellite, of the actual satellite, right before to move from UK to Germany, where it was testing for environmental testing, thermal, acoustic, all testing was accomplished in Germany. And then from there was moved in November 2019 to Florida, to Cape Canaveral Kennedy Center, where, you know, in Astrotech was the final integration of the spacecraft to the rocket and the launch. And here you can see the launch. At least I recommend you to, probably you have done already, to see in YouTube. Here it was a live experience for many of us. And we were watching obviously from outside, but we have here the camera that ULA incorporated in several parts of the rocket, and we can track from outside what is happening with the rocket, and inside all the, you know, things that are happening with the spacecraft. And here we can see the last image of the satellite when it started her journey to accomplish her mission. And
Dr.
these are,
Nieves, excuse me one second. I think that your microphone is scratching maybe against your shirt. If you could just pull it out a little bit,
sorry.
then yeah, no worries. I just wanted to make sure everybody could hear you.
Okay,
Thanks.
thank you. So, and here what you see is so part of the ESA team, experts in asteroid, that were tracking a solar orbiter from Earth. So this picture is also a picture that I took the night before to the land. I was just myself in the pad with this rocket, and it was, as I said, a life experience for me. So this is, so I took this, in this website, you can track the solar orbiter. I did a few minutes ago. In Europe is already 24th. So you can see here is a solar orbiter, here is the Earth, the distance between both is 1.49 astronomical units. And we just passed the first perihelion. It was on June 15. So, and the maximum approach that we reached this time was 0.5 astronomical units, in halfway between Sun and Earth. So during all this time from launch to June 15, around June 15, it was what we call commissioning activities. These commissioning activities is just the period of time where project manager, engineers, and scientists work together to switch on and calibrate the spacecraft and the instruments. During this phase, during this part, all the instruments were on. So before starting the cruise phase, even the remote sensing instruments were on, and we got images from these instruments. So now in September, just to mention before going to the first light images, in September, the in-situ data, so right now the teams are working in the calibration of the data, the in-situ data will be released to the public and the community to explore new knowledge in the space science. So, and here you can see the first images, the first light from the 10 instruments. Let me go, because when I talked before about connecting dots, you can see that with a solar orbiter, with these 10 instruments, we can go from small scales in the sun to big explosions in the sun, track all of them from the sun surface to the corona, and later the heliosphere, and eventually to touch them with the in-situ instruments. So let me start with the extreme ultraviolet imager. So this is measuring the wavelength of extreme ultraviolet, and is observing from the sun surface to the lower corona, and we can see there's the plasma movements and the activity in this area. So from here we can go to the polarimetric and helioseismic imager, the PHI instrument. The PHI instrument is going to provide information of the magnetic field in the surface of the sun, and eventually with a technique that is called helioseismology, we are going to be able to infer the movement of the activity right below the sun surface. So we are going to be able to track what is happening right below the track surface, all the way to the surface, and eventually in the lower corona. And this is going to be possible here. Let me see, because I have sticks right here. A stick is the X-ray telescope. Is going to observe in X-ray wavelength, obviously, and then it's going to be able to observe the most energetic activity in the sun. So if something happens like a flare, so X-ray, a stick is going to be able to observe. So, and if it's something happening right here, so like a big explosion from the sun, with the coronagraph, with METIS right here at the top right, the coronagraph is going to be able to provide information on the corona. So METIS is also very special, and I will show later some images, more images from METIS. Is very special, not just because coronagraphs are very usual in the community. We have several coronagraphs, but in this case, it's going to provide observations in two wavelengths, in white light and also in ultraviolet. And this is something ultraviolet wavelength never has been provided these observations to the community. So it's something very new and very interesting. And also because we are going to be very close to the sun, we are going to be observing, you know, areas in the corona never observed before. So more information because of the coronagraph is blocking the sun, the disk with the sun disk with the coronagraph. We are not observing the corona right in front, and that's why we have SPICE right here. SPICE is able to, it's a spectrometer that is able to provide information of the corona in the disk. So in addition to the information of the corona, is also providing information about the composition. And this is also very interesting because we usually observe the plasma movements, electrons, protons, helium but with this instrument we are going to be observing also heavy ions, and this is in connection. This remote sensing telescope is going to be very connected with one of the instruments in the solar wind analyzer that is going to be measuring this composition by the first time in the inner heliosphere. In connecting a SPICE, what we observe with the light, with we observe with the in-situ instrument. So as I say, we have big explosions with X-rays right here. So energetic particles are going to be injected into the heliosphere, and the EPD, the energetic particle detector right here, is going to provide the link and the connections between the remote sensing and the in-situ. And we have obviously a magnetometer. A magnetometer provides measurements of in-situ measurements of the magnetic field, which is amassed in an heliospheric observatory because of the magnetic field dominate completely the heliosphere. And then we will have also, and I don't want to forget, waves. Waves provide is an instrument in between remote sensing and in-situ instrument, because we are observing radio waves, but also we are observing plasma waves. So it is an instrument that link remote and in-situ instrumentation. So here is an overview of the first slide, images from our satellites, from Solar Orbiter. And here let me go in detail about some of the highlights of these images. Here we have a detail of the extreme ultraviolet instrument, the UI. So there are several sensors in this instrument. We have the full disk view that provide, you know, an overview that is what is happening in the sun. And then we have a high resolution detector that provides just parcels of the sun at a very high resolution. And because we are going to be very close to the sun, we are going to be able to resolve, you know, a small scale structure. And actually with this first slide, we have done so. So we have been observing, I'm going to be highlight one of the parcels here. We have been observing multitude of small flaring loops and features. We have dimmings, we have you know, the loops here, fibrils moving, and we have been, the instrument team has been observing and reporting to the science team in the mission this small increase, of intensity. So they were working from the beginning, very hard to try to see if it was something, from the instrument or the calibration issue. But they actually saw a lot of these small scale flares, let's say. They start to call them campfires, and probably you have heard about that. So, and why is important these campfires? So there is a long-standing question in our field. There is a region between the sun surface atmosphere and the lower corona that is called the transition region. In this transition region, the temperature in the area increase. So you will expect as you move away from the sun, the temperature decrease. Actually, after the transition region, the temperature decrease again. But just in this small area, in this small region, the temperature increase. And the scientists has been trying to explain this for years. And we don't really understand why the temperature, the plasma is heated too much in that area, in that region. So because UI is observing in that area, the team think, the hypothesis is that these are like small nano flares or small flares that in the flares there are a process of the magnetic reconnection, and in this magnetic reconnection there are release of energy, thermal energy that can heat the plasma. And it could be an explanation for this or an answer for this question. So we are looking forward, the scientists are working to prove that this hypothesis is actual, the right one. So we'll see in the next few months what we say. And here, just for illustration, one more, the color is arbitrary color, and because of the illustrate different wavelengths in the extreme ultraviolet. The one in yellow is 70 nanometers, and the pink one is 121.6 nanometers. In this wavelength, we are observing the granulation of the plasma because of the movement of the magnetic field in the sun surface. So as I say, here we have Metis. There are the 2 days. Here we have the colors are just white light in the case of green and ultraviolet in the case of the pink. The composition of the corona is very normal. Is in the minimum phase where we are rising out now to the solar cycle 25. So, and this is very interesting to see in different wavelengths. And here we have finally, as I said, we have the coronagraph, we have the UI, and then if you see the line right here below, we have the solar distance. This is coronagraph is gonna go to 5.8 solar radius, and from 10 solar radius to 85 solar radius, we are gonna have solo high. Solo high is the heliophysics imager that we are gonna allow us to track the structures all the way to the heliosphere. In this case, in the first image, from Solo High, we observe Mercury, and this increase of these white features right here are just because the team is still working in the calibration. This is the F corona, and this is a feature from the solar arrays that need to be removed eventually. So, just to finish, just thank you. But I want, before leaving you, I want to introduce part of the team. Is just part of the people that have been working for years in this mission. At the top, we have the project scientists in the NASA and ESA. This is the team, the NASA team, project team, or there is another team in the ESA. And right here in front of our rocket, Atlas 5, we have part of the science and instrument team the day before of the launch. Thank you very much.
All right, well, that's fantastic. This is really, really interesting. So we do have quite a number of questions here. And so I'm going to kind of go in reverse order. We've got some having to do with the instrumentation. Ron was wondering about, are the instruments always pointed at the sun regardless of the spacecraft's position?
So the spacecraft is the one which is pointing to the sun. So the instruments are all located, behind the heat shield. So it's very important to keep the pointing, very static, because we don't have to have, this kind of movement can expose the instrument to the sun flux that can damage to the instruments, and also because of the remote sensing instrument, the telescope requires some kind of stability in order to make the observations. Same as the telescopes when we use them here at the ground.
All right, so let's see. Related to that, and so given the heating problem, how long can the openings be open for each instrument to gather data? Is it on the range of minutes, hours,
So because they are protected, the instruments are going to be the remote sensing. The instruments that are right behind the heat shield, and they don't need to be looking at the sun. They are going to be always taking measurements. For those that need to look at the sun, they have their own protection. So during the 3 dedicated windows of 10 days around, they are going to be observing all the time. They are not, and actually the kind of material has been developed for this mission. The degradation of the material is very low, and they have been testing for years. And we are pretty sure that it's going to be for, lasting for the 10 years of the mission.
Yeah. So we also have a question here, and I know that you talked about this, but I'm not sure if you answered this specifically. So what's the main purpose of having the spacecraft out of the plane of the ecliptic?
This is a very important question that I didn't emphasize during the talk. So we never have seen the sun poles, never. So we don't know how they are. But why it's important to see and to look at the sun poles? Because they are playing an important role in the dynamic and the connections between the magnetic field. When I talk that the rotation in the equator and the poles are different, so it seems that there are an area around the poles that play a significant role in this kind of accumulation of energy. And by observing with these instruments, the poles, we are going to be able to better understand the solar model, the global model of the sun, how to generate the magnetic field. Mm-hmm.
All right. So here's an interesting question that a lot of people have been observing the comet Neowise, and I know that a lot of the older missions have observed comets, some of the sun-grazing comets. Were you able to observe this current comet with solar orbiter at all, or?
No, there was one comet right before the last one. It was called Atlas, and actually, if you allow me, let me go here. This is the comet. This is the Atlas. So we learned about this comet. It was about June 5th, I think, May 30, June 5th. And then we tracked the orbit of the comet and the orbit of our satellite. And we believe we were crossing the tail of this comet with solar orbiter. Still, we are gathering the data and trying to analyze that what we observed was part of the tail or is not. Still we are calibrating the data and learning about that. But it was very interesting. The comets are very interesting lately.
All right. So we have a few questions here about CMEs and the effect on our planet and others. And so we had a question, have we observed how the CMEs affect other planets or moons other than just the Earth?
Yeah, so actually there are many scientists trying to, obviously we have Mercury, which is, completely, devastated by the solar radiation and solar activity. But we have also learning about how Mars can be affected by the sun variability and the coronal mass ejections. So, and there are many theories about that. If the planet have been degraded because of the solar activity, but there are ongoing research to learn about how the sun variability affect to the planets in the solar system and in other solar systems also.
So here's an interesting question, and I'm guessing that it has to do with CMEs. If we had a really big CME hit Earth, could it potentially break our magnetic field? And if it did, could we survive?
I mean, if it breaks our magnetic field and take the magnetic field with it, we are gonna be just saying bye to this universe forever. But the point is, we can have a very strong coronal mass ejection, and this is a extreme event that I was talking about. These extreme events can, damage the magnetosphere and, allow the entrance of a lot of energy, and eventually, disrupt our lives, our satellites. So is the extreme events what are gonna bring is disruption in our technologies, but the magnetosphere is gonna stay there for a few more years, centuries.
That's good. So back to the sun's magnetic field. Speaking of magnetic fields, does one pole on the sun have a greater influence on the solar magnetic activity?
Say again?
Is there a difference between so yeah, on the sun's pole, is one of the poles dominant in the magnetic activity, or is it?
In fact, they change. So they change every 11 years. So the polarity is changing. So actually, I talk about 11 years solar cycle, but actually is 22 years of solar cycle because the polarity change every 11 years. So it's actually 22 years.
Okay, so we've got time for just a couple more questions, and then I know that we're after you're on the East Coast, so it's after 10. And so you said that we haven't looked at the poles, but one person said, well, didn't Ulysses fly over the poles? And so we had a view of it in the past, or
no, but
different?
Ulysses took in-situ measurements, not remote sensing observations. It didn't have telescopes to observe with light the poles. It's just in situ, I mean, taking measurements of what was around the spacecraft.
Ah, okay. So it really wasn't a solar observing mission.
No, it was more a heliospheric observatory.
Okay. Let's see. So let's go for one more.
Sure.
This will be the last question. So all solar probes after their service time, what are you going to do with a solar orbiter when it's done with its service?
So, we were talking because there is not a plan by itself. After 10 years, the agencies can, I mean, probably ESA is the one which is going to be making decision about that. So I don't have, and I was trying to explore because I knew that I was going to have this question eventually, but there is no plan for now.
Okay. Well, let's, here's to about 10 years worth of really good science. Go ahead and stop sharing your screen.
Okay.
Mine,
yeah,
so.
sorry. I have this.
All's good. It's been fun seeing the comet go back
Comet.
and forth there. So, Well, we've got a lot more questions, but it's well after time. And so we want to, be considerate of your time. Thank you so much.
I mean, you have my email. So if anyone is, want to make questions and talk with me or with a scientist, I'm very happy to keep talking later or another moment. Yeah.
And you had that at the beginning or the end at the end of your presentation?
Say again?
Was it in your slides? One of your slides had it on it?
I don't know. No, but I can put my. You want my slides?
I'm just wondering because we have the one that would be nice.
Yeah. So I can give you my presentation and then I can put my email, so you can use the movies and all this stuff.
Yeah, I just don't want to go sharing your email with the world if we don't, without your permission or something.
Yeah, I mean, it's in the website, in NASA website. You can see my email.
Okay.
So.
Okay.
Okay.
Well, great. We would love to have your slides, and so
Sure.
that's all for tonight, everyone. And thank you, Teresa,
Thank you.
for joining us this evening, and thank you, everyone, for tuning in. And so, everyone, you'll be able to find this webinar. It's going to be Monday now. We're not going to be able to get to it until after the weekend. So you'll be able to find this webinar along with many others on the Night Sky Network website in the Outreach Resources section. Each webinar's page also features additional resources and activities. And if we get your slides, we will be posting those up there as well. And this will also be on, since we've been live streaming, it automatically recorded, but we'll be updating that in the next few days as well with some links. And so you can also join us for our next webinar on August 25, when Dr. Cynthia Evans from NASA's Johnson Space Center will share with us how NASA is searching for meteorites in Antarctica. So we can go from a really, really warm place to a really, really cold place all in the space of a month. So it's so thank you so much again.
Thank you very much for having me. It has been a pleasure.
And thank you so much, Carolyn, for making the introductions and for joining us. And so we have one of the other NASA heliophysics team members here with us this evening too. So it's
you're very welcome anytime.
So
and thank you, Teresa.
All right.
Bye.
Well, thank you so much, and take care and have a great evening. And
You too.
Okay, bye.
Thank you all. Take care.
Dave, are you still there? Dave?
I am, yes.
That was weird all of a sudden, and I didn't get a chance to read what you had said